Okay, we're going to talk about the light-dependent reactions of photosynthesis. So the aim of the whole point of the light-dependent reactions is that you're going to generate you're going to generate ATP from ADP, an inorganic phosphate, and you're also going to generate NADPH. These are energy-rich compounds, as we've seen before, and they are going to be used to drive forward the reactions of the light independent reactions, sometimes called the dark reactions, which is probably not a good idea because they don't tend to occur in the dark, but you don't actually need light from there. Okay, so you've got to make ATP and NADPH. NADPH is very similar to NADH, which you've come across in respiration and oxidative phosphorylation and glycolysis and so on. Very similar. The only difference is it's got a phosphate group attached. Right, let's have a think then what's going on. Okay, so this molecule over on the left is chlorophyll. Okay, this is, as you know, is absolutely essential for photosynthesis. And if you notice, if you look at it, you've got a central magnesium atom there. This is extremely similar to the heme group. The main difference being that in heme you have an Fe2 plus ion in the center, whereas with chlorophyll you have an Mg2 plus ion in the center there. Now you can see the Mg has got 2 pluses on it there, and each of that nitrogen's got a minus and that nitrogen's got a minus on it. So the overall molecule is neutral, but those charges are not really sitting on those atoms. It's kind of spread over, the charge is spread over the whole thing. Okay, so right, I'm going to rub that out, sorry, and let us just think. If you look, if you do chemistry, you'll notice there's a lot of double bonds in this chlorophyll molecule, and you also know these double bonds, they're alternate, single, double, single, double. So that means you've got delocalized electrons in that system, like you have in benzene. Okay, you've got delocalized electrons. Now that means when light energy shines on it, when a photon comes, okay, so we can think of light as a wave or as a particle. Let's think of it as little photons, little packets of energy. When photons land on the chlorophyll molecule, because the electrons are delocalized, what you can do is you can knock an electron up to a higher energy level. So it's kind of like an excited state, and that means that the chlorophyll, which normally does not want to lose an electron, once it's absorbed a photon of light, it makes it, the electron gets promoted to a very high level, and it makes it very willing to lose an electron, which you may think, remember, that makes it a reducing agent, but it needs a photon to do that. Okay, so that's enough about chlorophyll. Now let's think about the chloroplast. So a diagram of the chloroplast we've got here. These stacked green things are called thylakoids, which you probably know about. And here, this is the stroma. So that is where the light independent reactions occur. So that's where you've got your rubisco and those enzymes. Yeah. And the thylakoids, that they are made of membranes. There's actually 3 membranes in a chloroplast. There's this one, there's the outer membrane. This one is the inner membrane. And these green ones are the thylakoid membranes. And the thylakoid membranes is where all these reactions of the light-dependent steps occur. They occur in the thylakoid membranes. You've got a lot of enzyme complexes in there. You've also got chlorophyll molecules in there, lots of chlorophyll. That is where it's all happening, is in those membranes. So if you've done respiration, the inner membrane of the mitochondria is very important for oxidative phosphorylation. That's where it all happens. This is extremely similar situation here. All these reactions occur in the thylakoid membranes. Okay, so we have 2 light capturing complexes in chloroplasts, and they are called, imaginatively called photosystem 1, and that's P680. That's because it absorbs light at 680 nanometers, and P700, which absorbs light at a slightly higher wavelength, 700 nanometers, slightly lower frequency, and each one does a slightly different job. But what happens is, with each of these, they're both associated with antennae pigments. Right, so that's lots of molecules of chlorophyll, other molecules of chlorophyll, and things like vitamin A, carotenoids. And what these do, the antenna pigments absorb photons, and they pass the energy on to the reactive center, okay, of those. Now at the reactive center, you have two molecules of chlorophyll in each one. So the antenna pigments, they act like they sort of like gather in all the photons. They don't absorb the energy of those photons. They just pass the energy straight on to the reactive center. Okay. Now, what happens is once the reactive center absorbs the energy, photosystem 1 or photosystem 2, what happens is they lose an electron. And moreover, they pass that electron on. So let's just have a look, see what happens here. Right, so here we've got, this is called an electron transfer chain, which if you've done respiration, we'll come across in the mitochondria. Electron transfer chain. Now, just remember GCSE chemistry, oil rig. Oxidation is loss, reduction is gain of electrons. So in an electron transfer chain, you have two versions of every, of each carrier. When it's got the electrons, when it's got electrons, it's reduced, and it can give those electrons away to the next thing in the chain, and it becomes oxidized. So imagine you start off with this reduced thing here, it passes an electron, or usually it's a pair of electrons. Okay, so the electrons get passed on to the A oxidized, which will turn that into A reduced. Now the A reduced doesn't hang on to those electrons, it passes those electrons on to the B oxidized. So those electrons will be passed on to the B oxidized down there, which of course will then, when it gains those electrons, become B reduced. They pass it on to C and so on here. Okay, now the final member of the electron transfer chain is the oxidized form of NADP. So that's called NADP plus. That hasn't got a lot of chemical energy stored in it. The electrons get passed onto it and turn into NADPH. This is the reduced form. This is a lot of chemical energy in that, and that is used to drive forward the reactions of the light independent things, which then occur in the stroma of the chloroplast, whereas this electron transfer chain, that's happening actually in the thylakoid membrane. Okay, so electrons are being passed on from these two photosystems down the chain. Okay, we'll have a look at the order of those, how it's passed on in a bit more. But let's talk about the source of these electrons. Right, at the end here, we get electrons being given away. So that means at this end of the thing, you've got to have electrons coming in. So what's the source of those electrons? Well, that is explained by this question here. I've written O2 liberated. We know in photosynthesis, oxygen is released, isn't it? Okay. Now, where the source of those electrons are those ones down there. Okay. So what happens is, let's have a quick look here. Let's have a look at this. Is actually photosystem 2 only, right? So this absorbs a photon of energy. As a photon comes in there. That causes photosystem 2 to lose an electron. And where does that? That goes into the electron transfer chain. And ultimately gets passed on to NADP plus, yeah, that's what, to make NADPH ultimately. But if this PS2 loses an electron, right, that would make it positively charged, and that electron is going to be replaced. Okay. Now, when this becomes positively charged, after it's lost an electron, it will become very, very good at drawing in electrons. In other words, it's a very good oxidizing agent. It's so good at pulling electrons in that it actually can pull electrons off water, which is very difficult to do. Water normally never just falls apart into oxygen, hydrogen ions and electrons. Can you see there? It would never normally do that because that would be very endothermic. But because when this is lost an electron, the photosystem 2, it's very good at pulling electrons off things, and it can even pull them off water. Okay. Now let's have a look at this electron if you're not familiar with these, if you don't do chemistry still. Well, that equation is balanced. You can see it's balanced with respect to hydrogens, with oxygens, and with respect to charge. So you've got 4 positive charge, 4 protons. So that means you've got to be releasing 4 electrons, negative electrons there. Okay. So you've basically split water up and you've made oxygen. A little bit of a problem there is when you shine a photon onto photosystem 1, it's only going to loses 1 electron, whereas we need to lose, this one gives away 4 electrons. So you have a little intermediary here. Okay, so those electrons, what happens is you've got this enzyme with a manganese atom here. Manganese atom is a transition metal. It's very good at very good at losing electrons, getting them back, losing them again, getting them back, and so on. That's how they act as catalysts, quite often transition metals. So you've got a manganese atom there. What it will do is every time the photosystem 2 loses an electron, the manganese will give an electron to the photosystem 2 until it has lost 4 electrons. Once it has lost 4 electrons, then it grabs 4 electrons off water and generates a molecule of oxygen. So it's like a sort of electron bank, and then when it's ready, it grabs all 4 off the water. Photosystem 2 is losing an electron 1 at a time. This manganese just helps it help do that. Right, let's put the whole thing together now and let's see how that works out. Okay. Right, so we go down here. Right, now this is my mitochondrial. This is my thylakoid membrane. Okay, so this is the thylakoid membrane, and this will be the inner thylakoid space. So that's inside one of those little discs, those little green discs in a right. And out here we have got the stroma, the site of the dark reactions. This is the lipid bilayer, right? This I've drawn here, and of course these big blobs I've drawn in it are proteins or protein complexes of some sort. Now this one here is photosystem 2. So this is photosystem 2. We said that absorbs a photon of light and loses electrons. As it loses electrons, what it does, it takes, so you're going to have 2 H2O, and that's going to split up into O2 and 4H plus and 4 E minus. And those E minuses, right, so they're going to go into photosystem 2, and they get passed on to this yellow thing here, which is representing one of the members of the electron transfer chain. There's actually several different members, I've only drawn one. And this is very similar to the mitochondria happens here. What happens is when this yellow electron transfer component, which is actually called cytochrome BF, don't worry about that. When it gets reduced, it takes on some protons from the outside. Takes on 2 protons. And then when it gives its electrons on to the next member of the chain, the next member of the chain is actually photosystem 1. When it does that, those electrons end up getting pushed over to the other side of the membrane. They get pumped across the membrane. So 2H plus. So you can see here, when the electrons are transferring, we're ending up creating a gradient in the concentration of protons. So the proton concentration in the stroma is going to decrease, and the concentration in the inner thylakoid space is going to become higher. It's more acidic on this side here. Okay. Now this is also helped by this process here, because look, every time you split up a molecule of water, you get 4 protons here. So you can see that in this space, it's going to become more. Hydrogen ion concentration is going to increase. And the hydrogen ion concentration in the stroma is going to decrease. Right, the electrons are passed on from this yellow transfer chain, as we said, to photosystem 1. Now, photosystem 1, well, a photon shines on that. Need a bit more energy in here, and so this is a photon. So photosystem 1 will lose an electron. The hole that electron leaves, photosystem 1 will possibly be filled by the electrons coming in from there. And then photosystem 1 passes the electrons onto these members of the electron transfer chain. And there's several different members. I've drawn 2, there's more than 2. Finally, it comes to an enzyme called ferredoxin, which is on the outside. And ferredoxin then passes the electrons onto NAD plus, NADP plus, sorry, and it will turn it into NADPH. And you probably it hasn't escaped your attention, I'm sure, that you need an H plus there also. So that means that we're using up H pluses on the stroma, so that also helps the concentration of H plus ions, helps the gradient, so you end up with less on the stroma side and more on the inner thylakoid side. So you've made your NAD. So we've seen how you've made NADPH there, which is needed for the dark reactions. What about the ATP? Well, the ATP is made from this proton gradient. Here, this huge complex I've drawn here on the membrane, this is called ATP synthase. And what happens is protons will diffuse down the concentration gradient. So they're going to go this way because you've got a high proton conc here, H plus conc, and you've got a lower concentration here. So the hydrogen ions are all going to diffuse through. Right, that is, that's downhill in energy terms, that's exothermic, and the energy of those protons is used to create ATP there. So what happens with this molecule? You get ADP plus inorganic phosphate, and it turns it into ATP, and the ATP is then used in the dark reactions. Okay, so let's have a look at the overall reactions in the overall what is happening in the light-dependent reactions. Right, it's all about electrons moving, isn't it? Okay, electrons are transferred. And you start off with NAD plus, which hasn't got any electrons. Sorry, that should be NADP plus. And the oxygen is the one that gives it electrons. Sorry, H2O is the one that gives its electrons. And that is going to turn it into NADPH. And you're going to get oxygen gas. And I know that NADPH, sorry. That equation is not balanced. Don't worry too much about that. But the important thing is the electrons are passed from the from the water. It loses electrons, and this gains electrons. Now that reaction, if you've got water and NAD+, there's no way they would react together, because this reaction here is very endothermic. The reason why it can happen, of course, is because you get the input of photons, and they've got that's energy. So the photons carry energy into the system, and that's through PS2 and then through P photosystem 1. And in the process of moving the electrons along, you generate a proton gradient, an H plus concentration gradient, and then those hydrogen ions pass through this ATP synthase enzyme, and this will generate ATP. The ATP and the NADPH, which are made in that reaction, are then used in the dark reactions of the light-independent reactions.